This is Unit 6, Video 1. In this unit, we will study gases, a very important area of chemistry because it gives us a glimpse into compounds. In fact, one of the early ways to determine molar masses of compounds, which is extremely important, these are the ones that appear in the periodic table, was by studying the gaseous form of that chemical. So gases are very important. Let's begin. So the characteristics of gases, and we're going to contrast them with liquids and solids. Gases expand to fill their containers. So if you have a little bit of a gas and you put it in a big container, it will fill the entire container. They are highly compressible, which means you can squeeze them into a smaller container, and they have extremely low densities as compared to liquids and solids, more than 1,000 times lower as compared to the other two states. Now, these properties result from gas particles having no intermolecular forces. This will be a key feature of gases. There are no attractive forces between the gas particles. Now, in liquids and solids, this attractive force does exist, but with gases, it does not exist. And that's why they are gases, and they can fly everywhere, because there are no forces between the molecules. Now, the theory that kind of sets the stage for us is called the Kinetic Molecular Theory of Gases, or the KMT, and this is a model that aids in our understanding of gas properties and behavior. So essentially it describes the behavior of ideal gases. So here with the term ideal we mean perfect gases. And as we'll see later on, not all gases are perfect, and there are some gases that are more perfect than others. For example, hydrogen is a much more perfect gas than, say, sulfur dioxide, even though both are gases. Hydrogen behaves much more like an ideal gas, and sulfur dioxide not as much. So we're going to go through four what are called postulates of the kinetic molecular theory, 4 points or 4 statements or assumptions. The first assumption is that gases consist of a large number of particles which are moving in a constant, rapid, random motion. So any sample of gas, the particles are constantly in motion, extremely rapid, and in fact their speeds average about 1,000 miles per hour, which is faster than the speed of sound. They are pretty small, and they're constantly colliding with each other, and that's kind of the idea. This is the picture of gases that you should have in your head, the gas particles moving around like crazy. The second assumption says that gas particles have no volume. They don't take up any space. What this means is that if you have a container like this, you have a bunch of gas particles in there. Now these particles are so small, here they're drawn to be big enough for you to see them, but in fact they are so tiny that obviously they're too small to see, but they're so tiny that their volume, if you were to collect all the gas particles and say put them in the corner, just stick them all in the corner, they would take up such a small volume, they'd actually take up much less volume, just a tiny portion of the volume of the whole container, to where we can say that we can ignore that volume that they take up. So we say essentially the container is really just empty space. The volume of the particles is negligible. That's the idea. And this is why gases can be compressed. You can compress a gas all the way down to a really, really small point. You can actually compress them down into a liquid is what you can do. So the gas becomes a liquid, and that's about it. You can compress them slightly more into a solid sometimes, but the volume won't change by too much after that point. That's the second assumption. The third assumption says there are no attractive and repulsive forces. This was kind of the key definition of a gas. So no intermolecular forces. So no forces here. In truth, these forces do exist. However, they are so negligible that we ignore them. In fact, forces exist between any molecules. But here, you can think of it this way. The gas particles are moving around so fast that this force can be ignored. This force doesn't affect their behavior. That's the idea. Now, if this force was there, again, then the gas would become a liquid or even a solid. So we assume that these intermolecular forces, these are the IMFs, are absent. No IMFs with gases. And the last assumption is that gas particles have what are called elastic collisions. Now, elastic collisions is a fancy word for saying that the collisions don't lose any energy. So here it says energy can be transferred between the collisions. So for example, if one particle hits another particle, this particle was going faster and this was going slowly. Now this particle can actually start going fast and in a different direction, but the average or the total kinetic energy does not change, which is kind of strange. Anytime you do this with bigger substances like billiard balls, the energy always changes, or actually the energy always slowly disappears or is slowly reduced. It's actually transferred into heat energy and sound energy and friction energy with the table and so forth. So eventually these billiard balls slow down, but with particles, because they're so tiny, they never slow down, which is a bit strange. But the particles just keep moving at the same speed, overall at the same speed as they were to begin with. So those are the four postulates, the four statements about gases. Now, here it says, let's take a note before we finish. Real gases follow these assumptions under what are called ideal conditions, but not under extreme conditions. So for example, if you have a gas in a container, or in like these balloons right here, and the temperature is pretty mild, say the temperature, you take 22 degrees Celsius, which is room temperature, and the pressure, we'll say, is 1 atmosphere, which is roughly a room pressure. So these gases will behave under these four assumptions. They don't have any attractive forces between them. You can ignore their volumes, and so forth. But if you were to increase the temperature, or rather reduce the temperature, usually if the temperature gets reduced all the way down to like negative 180 degrees Celsius or something, or if the pressure goes up really, really high, say to 200 atm or something, these conditions will be called extreme conditions, and then you cannot use these assumptions. At these conditions, for example, gas particles do have attractions for each other. The temperature is so low that they attract, their movement causes their attraction to have an effect. And they're so close together that you can't really ignore the volume. You can't, there's so many particles essentially, you can't ignore the volume. And that's the idea. So usually under very high pressures and very low temperatures, these assumptions break down. So the gases are called ideal if they're under ideal conditions. Now, ideal conditions, say if you are at 300 degrees Celsius, that's still ideal conditions. Even if you're under maybe 100, or not 100, maybe 15 atm or something. As you'll see, these are pressure temperature units. You could increase the pressure and change the temperature by quite a bit before the ideal conditions disappear. And this again depends on the gas. Some gases, like hydrogen, take a really, really high pressure and really, really low temperature for it to stop being a gas. Other things like sulfur trioxide, much more mild conditions will get you to that point. All right, so this wraps up for us the first video